Look up at the night sky. What do you see? Thousands of twinkling stars, right? Now imagine each of those stars as a giant ball of burning gas, a cosmic furnace where matter is transformed into energy. These celestial bodies, scattered across the vast canvas of space, are not static points of light. They are dynamic entities, engaged in a continuous cycle of birth, life, death, and rebirth. From the smallest, faintest stars to the most massive and luminous, each plays a crucial role in the grand cosmic drama. Their births ignite the flames of creation, seeding the universe with the building blocks of planets, life, and even ourselves. Their deaths, often explosive and dramatic, scatter these elements far and wide, enriching the interstellar medium and paving the way for new generations of stars and planetary systems. By observing stars at different stages of their lives, astronomers have been able to construct a detailed narrative of stellar evolution, from the initial collapse of a cloud of gas and dust to the eventual fate of a star's core. This narrative is constantly being refined as new discoveries are made, pushing the boundaries of our knowledge and challenging our understanding of the universe we inhabit. In this cosmic ballet, stars are not merely passive players, but active participants, shaping the galaxies they inhabit and influencing the evolution of the universe itself. Stars, like humans, are born, live, and eventually die. Their birthplaces are vast, cold clouds of gas and dust scattered throughout galaxies. These stellar nurseries, often called nebulae, are the cosmic cradles where stars take their first breath. Imagine a cloud of smoke, but on a cosmic scale, stretching for light years across the emptiness of space. These clouds, composed mostly of hydrogen and helium, the lightest elements in the universe, are the raw materials from which stars are born. Gravity, the architect of the cosmos, plays a crucial role in this stellar genesis. Over millions of years, gravity draws the gas and dust in these nebulae together. As the cloud collapses, it begins to spin, like a figure skater pulling their arms in. This spinning motion further compresses the core of the cloud, causing it to heat up. As the core continues to contract and heat up, it eventually reaches a critical temperature, about 10 million degrees Celsius. At this point, the hydrogen atoms in the core begin to fuse together, forming helium and releasing an enormous amount of energy. Once a star achieves nuclear fusion, it settles into a long, stable period known as the main sequence. This phase, much like the prime of a human life, is where the star spends the majority of its existence. Our own sun, a middle-aged star, is currently enjoying its time on the main sequence, radiating energy and providing the light and warmth that sustains life on Earth. During this phase, a star exists in a delicate but stable equilibrium. Gravity, relentlessly trying to pull all the star's material towards its center, is counteracted by the outward pressure generated by nuclear fusion in the core. The length of a star's main sequence lifespan depends largely on its mass. Massive stars, like cosmic rock stars, live fast and die young. They burn through their hydrogen fuel at a prodigious rate, shining brightly but exhausting their fuel reserves relatively quickly. Smaller stars, on the other hand, are the cosmic marathon runners. They sip their hydrogen fuel slowly and steadily, extending their main sequence lifetimes for billions, even trillions of years. As a star ages, its hydrogen fuel, the lifeblood of its nuclear furnace, begins to dwindle. Like a car sputtering on fumes, the star's energy output starts to fluctuate. The delicate balance between gravity and fusion, maintained for eons, begins to waver. With hydrogen in the core depleted, the star's core contracts under its own gravity, heating up even further. This increased heat triggers hydrogen fusion in a shell surrounding the core, like a ring of fire encircling the dying embers. This shell burning generates even more energy than before, causing the star's outer layers to expand dramatically. The star, once a compact and efficient furnace, now balloons outward, transforming into a red giant. Red giants are truly enormous, dwarfing their former main sequence selves. Our own sun, when it eventually exhausts its hydrogen fuel, will expand to become a red giant, engulfing the orbits of Mercury, Venus, and possibly even Earth. The fate of a star, whether it ends its life with a whimper or a bang, is determined by its mass. While smaller stars, like our sun, eventually fade away as white dwarfs, massive stars meet a far more dramatic end, a supernova explosion. These cosmic fireworks displays are among the most energetic events in the universe. outshining entire galaxies for a brief, brilliant moment. For massive stars, the core contraction and shell burning that characterize the red giant phase do not stop with helium. As the core continues to contract and heat up, it ignites the fusion of heavier elements: carbon, oxygen, neon, magnesium, silicon, each stage releasing less energy and lasting for shorter periods. The star becomes a cosmic onion, with layers of different elements fusing at different temperatures. This process of nuclear fusion continues until the core is primarily composed of iron. The aftermath of a star's death is as fascinating as its life. Depending on its initial mass, a star leaves behind a stellar remnant, a cosmic relic of its former glory. For stars like our Sun, the end of the red giant phase marks the formation of a white dwarf. As the outer layers of the star drift away, they form a planetary nebula, a glowing shell of gas and dust illuminated by the white-hot core at its center. This core, a white dwarf, is incredibly dense, packing the mass of the Sun into a sphere roughly the size of Earth. More massive stars, those that end their lives as supernovae, leave behind even more exotic remnants. If the core's mass is between 1.4 and 3 times the mass of the Sun, it collapses into a neutron star. Black holes, often portrayed as cosmic vacuum cleaners, are regions of space-time where gravity reigns supreme. Their gravitational pull is so intense that nothing, not even light, can escape their grasp. Imagine a waterfall, cascading endlessly into an abyss from which nothing returns. That's a black hole, a cosmic vortex where the fabric of space-time is warped beyond recognition. Though invisible to telescopes that detect light, black holes reveal their presence through their interactions with surrounding matter. As gas and dust spiral towards a black hole, they form an accretion disk, a swirling whirlpool of material heated to millions of degrees by friction. This superheated material emits intense X-rays detectable by space-based telescopes, providing evidence of the black hole's hidden presence. Black holes are not just cosmic gluttons, indiscriminately devouring everything in their path. They play a crucial role in the evolution of galaxies. The study of stellar evolution is a dynamic field, constantly evolving with each new discovery. Recent advancements in telescope technology and observational techniques have provided unprecedented views of the cosmos, allowing astronomers to witness stellar events in unprecedented detail and refine our understanding of the universe's grand narrative. One such discovery is the detection of gravitational waves from merging neutron stars. These ripples in space-time, predicted by Einstein's theory of general relativity, were first detected in 2017. The event, observed by both ground-based and space-based telescopes, confirmed that neutron star mergers are responsible for creating heavy elements like gold and platinum, enriching the interstellar medium with the building blocks of planets and life. Another groundbreaking observation is the first-ever image of a black hole, captured in 2019 by the Event Horizon Telescope. This remarkable achievement provided direct visual evidence of these enigmatic objects, confirming their existence beyond any doubt. While we have made remarkable strides in our understanding of stellar evolution, many mysteries remain. The universe, it seems, is full of surprises, and each answer often leads to more questions. One enduring mystery is the origin of supermassive black holes. These behemoths, found at the centers of most galaxies, have masses millions or even billions of times greater than our Sun. How these objects formed so early in the universe's history, when galaxies were just beginning to take shape, remains an open question. Did they form from the collapse of massive gas clouds? Or did they grow gradually by accreting surrounding matter? Unraveling this mystery will provide key insights into the early universe and the evolution of galaxies. Another puzzle is the nature of dark matter and dark energy, two invisible components that make up the vast majority of the universe's mass and energy budget. The study of stellar evolution is not merely an academic pursuit. It's a profound reflection on our place in the grand scheme of the cosmos. As we delve deeper into the lives and deaths of stars, we gain a deeper appreciation for the interconnectedness of the universe and our own existence within it. The elements that make up our bodies, the air we breathe, and the earth beneath our feet were all forged in the nuclear furnaces of stars. We are, in a very real sense, stardust. The atoms that constitute our very being were once part of a star, participating in the cosmic dance of fusion and creation. By studying stars, we gain insights into the fundamental laws of physics that govern the cosmos, from the smallest subatomic particles to the largest structures in the universe. Each new discovery brings us closer to understanding our place in the grand tapestry of the universe, fostering a sense of wonder and humility in the face of the vastness and complexity of the cosmos.